All right, great. So, hello everyone. It's an absolute pleasure to be here today. My name is Ashley Bock, and I work in the Alternative Fuels Laboratory at McGill University in Montreal, Canada. Our research focuses on metal fuels, and today I'm going to be presenting to you a techno-economic assessment of using aluminum, magnesium, and zinc metal as clean energy carriers for the future. So let's start this off with energy carriers in general. When talking about energy, it's not usually consumed at the same location where it's generated or found. Typically, you're going to have locations of very high supply, and thanks to global energy trade, it gets distributed far and wide to locations of demand. But this trade wouldn't be possible without energy carriers, which you might more commonly know as diesel, electricity, or more recently, hydrogen, ammonia. These are all materials which can hold energy and allow us to controllably move it from one location to another. Looking forward towards the green transition, the discussion around energy carriers becomes even more essential. For renewable energy resources like solar, wind, and hydro, which have inherent geographic restrictions and seasonal variability, we need new energy carriers to be able to depend on them entirely. These energy carriers need to be easily transportable over large distances and capable of storing large quantities of energy for long periods of time without any loss. Ideally, they are also safe, affordable, and most importantly, non-emitting over their entire life cycle. This is where I would like to introduce a new potential clean energy carrier that meets all of these criteria, and that's metal fuels. So how would that work? How could you use metal as an energy carrier? Well, the first step would be producing it using typical industrial standards, which in the case of aluminum, magnesium, and zinc would be electrolysis. This process uses electricity to transform metal ore into pure metal and is already set up on a global scale. In our case, we're going to want metal powders or small pellets seen here, and this is going to be our fuel. This metal holds energy, but under typical conditions, like we know, is completely unreactive, making it safe and easy for transportation and storage. To avoid emissions, this process would ideally occur at a location with an excess amount of renewable energy that we would be able to cheaply use to power our electrolysis process. Our metal, which contains energy like a battery, could then be shipped to another location where there is a demand but maybe no renewables, for example, a remote community. And there we will set up a metal fuel reactor in which our small pellets can be combined with supercritical water to spontaneously produce energy in the forms of hydrogen and heat. The only other reaction product would be the oxidized metal, and this is actually a key component in the circularity of metal fuels. This product can be sent back to the same electrolysis facility and using only renewable energy recharged into its metal form. So, in other words, this whole system works on a fixed quantity of metal, which allows us to transport energy from one location to another indefinitely without any emissions and ideally no material loss. Now, this doesn't work for every metal, but I can explain to you why magnesium, aluminum, and zinc were selected in particular. We start here with the full range of possibilities, being the periodic table of elements, and we're going to go based on process of elimination for some characteristics of an ideal energy carrier. So we need our fuel to be reactive with oxygen, lightweight, non-toxic, not too rare, non-polluting, have a high energy density, and then also have a controllable reaction with water, but still producing high metal-water reaction rates. And this is how we got to our theory. I went through that quickly on purpose to save time for the techno-economic part, but what I really want you to take away is that this choice is not random for these three metals. So one of my colleagues, Pascal Boudreau, has already looked into aluminum. Graphed here, he compares power to X costs of aluminum to diesel, hydrogen, and ammonia. The yellow stripe you see is the range of electricity costs obtainable using renewable energy sources, and within it, aluminum is in a comparable range to the other alternatives. He found that the cost of the reduction process to recharge aluminum greatly outweighed the cost of the metal itself and the transport and storage costs, which in themselves were pretty minimal due to the safe and stable nature of metals. With respect to the electrolysis process, it's a little different for every metal, but across the board, it's pretty much the same. The current Hall-Héroult electrolysis process used for the reduction of aluminum is affordable, but it currently emits a large quantity of CO2 because of the carbon anode, which gets consumed during the reaction. There all are alternative non-emitting anodes in works, but none of them are yet in commercial operation. And this has piqued our interest into furthering this analysis to include magnesium and zinc, to see if they would be comparable in cost to aluminum, but also maybe possess some advantages in terms of emission. So we know already that at least the electrolysis process is going to be different, but that's actually not the most important factor. Each metal contains different amounts of embedded chemical energy per ton. And this is the energy that is stored in the metal and will be released as heat and hydrogen when it's oxidized in our reactor. The hydrogen generated determined by the equation above, where M is any of the three metals, and XY are coefficients based on the number of valence electrons and the chemical equilibrium. The heat generated is determined by the enthalpy of formation of the oxides. Using a metal water reactor, both of these would be useful energy. The difference in the total amounts show that the stored amount of energy would vary differently depending on the quantity of metal. Assuming aluminum as a baseline, we're going to need 1.25 times as much magnesium and then 5.8 times as much zinc. In terms of our assessment, this factor is going to greatly affect all four of our cost categories. That being said, for transportation and storage, even with larger quantities of metal, it's found that proportionally those costs are still pretty minimal compared to the other expenses, so we're not going to get too much in depth into those. In Pascal's aluminum assessment, he assumed some dry bulk storage similar to a type of grain silo, and then a basic cargo ship would be sufficient, and we're going to go with the same. The next cost category is the metal fuel cost, and the difference in embedded energy does affect this more greatly. So metal fuels, like we were talking about, work circularly, which means none of it is actually consumed, and by the end of the cycle, you'll end up with the same metal that you started with. Therefore, it makes more sense to account for the metal as an item of inventory rather than an expense. And instead, we're going to be accounting for the cost of any metal lost in the system. So this would typically happen following the metal-water reaction in the separation system, and we're going to assume it's going to be about 1 to 3%, but could ideally be brought down to 0 with an effective system. So now that we have that all covered, we want to get into the most expensive cost that we were talking about, which is the electrolysis process. So electrical chemical reactions are used in producing a lot of the world's metal. For electrolysis, in general, you're going to have a cell that's filled with an electrolyte containing your metal oxide dissolved in either water or a molten salt. Spiritual inside, we're also going to have two different electrodes connected by an external circuit. So how this works, electrolysis uses an electrical current to move ions between these two electrodes. When a current is applied, positively charged metal ions move towards the cathode, where they're going to pick up an electron generated from the oxygen at the anode. As a result, our metal is going to be deposited at the cathode and oxygen gas generated at the anode. The details of this reaction vary for each metal, but in general, it consumes a significant amount of electricity. We're now going to look into the specifics of magnesium and zinc electrolysis to get a better understanding of where their costs are coming from. For the reduction of magnesium, there are actually two options, either a molten salt electrolytic process like the ones I just described, or a thermal process. The most common at the moment is actually a thermal process known as the pigeon process. It is cheap, but also very energy intensive and produces a lot of emissions. So for the purpose of this analysis, that's why we've done with an electrolysis method. So the electrolytic processes do still produce a lot of the worldwide magnesium, typically starting from a magnesium chloride, which then gets reduced by a molten salt electrolyte, producing undesirable chlorine gas emissions. Still not ideal, but as always, techniques are continuously being improved, such as with the solid oxide membrane electrolysis, which will be the method modeled in this analysis. Zinc, on the other hand, the main production technique is actually the electrolysis one, and it is the majority of the worldwide production. Zinc can be produced at low temperatures in an aqueous electrolyte and without any direct carbon emissions, thanks to an aluminum cathode. Though there is still the drawback that it requires a low current density, meaning more energy overall, since any higher would favor the production of hydrogen over the reduction of zinc. The full process has many steps, as you can see here. We go from purified zinc ore all the way to pure zinc metal. But for our metal fuel process, we would be able to cut out the energy-intensive roasting step and put our oxides directly into the leaching process. Now that we have an overview of these two processes, we can compare them to the reduction process of aluminum looked at in the earlier paper. In terms of voltage required, we see here they're all within the same range, with the zinc being slightly lower. For operating temperature, on the other hand, they are wildly different, since, as we remember, zinc is being reduced in an aqueous electrolyte versus magnesium and aluminum, which require a molten salt. So this molten salt leads to much higher energy consumption per ton of metal produced for aluminum and magnesium to keep the cell at a suitable temperature. In our context, this is going to be the amount of electricity required to charge our metal. Then we have the specific energy of the metal, which is what I produced earlier, which is the energy that can be discharged as heat and hydrogen once it's reacted. From here, we could get our chemical efficiency of the fuel, seeing it as 53% for magnesium, 49% for zinc, and 66% for aluminum. One great property of metals is they won't react or lose any of their charge until they're brought to the appropriate conditions in the reactor. This means that unlike batteries, which can discharge over time, metal fuels will keep the entirety of their charge as all the way stored until it's needed. Coming back to our total electricity costs, the electrolysis production requires electricity, obviously, but also facilities, operations, and other consumables. We have graphed here on 3 different axes the recharging costs per ton of magnesium, zinc, and then aluminum. They have been divided into categories, being the CapEx and the OpEx of the reduction facility, the electricity, consumables, and other costs. The consumable cost here does not include the cost of the oxides, since, as mentioned earlier, with our circular metal fuel, we'll be considering it as an inventory rather than an expense. At low electricity prices, it becomes clear that most of the cost is from the capital and operational expenses of the facilities. Here you see those 3 metals graphed on the single axis. In terms of producing a ton of metal, zinc and aluminum are comparable at low electricity prices, with magnesium reduction being slightly higher. But at this point, I'll remind you that we're actually looking for the best energy carrier, which means we don't want to produce the most tons of metal, but we want to be able to contain the most embedded chemical energy. So we're going to need to divide by the contained chemical energy of each metal. So we switch from a per ton basis to a per megawatt hour basis. And this is way more meaningful when talking in an energy context. Here we see that actually zinc is the most expensive per megawatt hour due to the fact that it can store much less energy per ton than magnesium and aluminum. Magnesium lies between the two, but is still significantly more expensive than aluminum. For magnesium, even if we were to reach the current industry gold standards of producing at 1.2 times the cost of aluminum, it'll always be more expensive on an energy basis since it contains less energy per ton. Putting this all back together, let's get back to our objective. Let's see what the cost of magnesium and zinc as metal carriers to be as competitive with aluminum. As assumed, per megawatt hour of energy, the transportation and storage costs are very minimal. The metal fuel cost is higher for zinc since more metal is required as it's less metal, and therefore more metal, more potential loss. Though in all cases, it's still the production process which greatly dominates the cost. Here we see those same values graphed depending on the input electricity price. Considering renewables, we'd be looking at the range from about $25 to $40 per megawatt hour. And magnesium at that price ends up being approximately 2 times the cost of aluminum and zinc 3.5 times the cost. This breakdown shows the significant impact of the cost would be the capital expenses of the facility. Though these facilities are currently producing metal from ore, not from the super pure metal oxides we would be obtaining in the reactor. Therefore, we can suspect that maybe a part of these costs and the operation would no longer be required. To enable the metal fuel economy, it will be essential to further dissect and analyze the costs associated to electrolysis in order to just refine it to the specific operations needed for metal oxide reduction. Also, getting entirely rid of that yellow bar, which is the cost of the loss. The lost metal will directly decrease. This can be accomplished using an effective separation system, following the metal-body reaction, and is certainly what I'm working on. Lastly, it's important to notice and monopolize on advantages less directly related to costs. For example, the low temperature operation of zinc make it more suitable for the variability of renewable energy, and it's currently the only one of these three metals that is an established primary electrolytic process with no direct carbon emissions. So in conclusion, magnesium and zinc may not currently compare economically to aluminum as a competitive energy carrier, but refining and optimizing the system to suit metal fuel might bring them closer to being so. For the moment, our lab continues to focus on aluminum and the design and development of a continuous flow metal water reactor, which would make it possible to deploy metal fuels as energy carriers at scale. I'd like to thank you all for your time and attention, and I'll be happy to take any questions. Thank you.
Thank you very much. Any questions?
Thank you, guys. Definition was curious about all like the solves and the options in that sort of costs that would involve putting that in the right vacuum or flush or naturals things that they're not like that while storage or maybe
Yeah, for sure. So that's a great question. It's actually already a characteristic. I mean, we're surrounded by aluminum and magnesium every day. Because of the oxygen in the atmosphere, a certain protective layer makes it naturally so that they won't react under conditions. So when I'm talking about aluminum, you could really think of just a piece of aluminum you could touch and handle. And it's only under the supercritical conditions in our metal reactor that that protective outer layer would kind of be progressively destroyed so you could react it all the way through. So no processing of any special kind would be required.
I just one short question. I've actually never come across this subject before, so it's really interesting to me. Whether it's threats that the transmission power actually is global, it's it actually that even if you want to transfer larger amounts, that's still really possible and the transportation costs remain the so.
Yeah, with the assuming of the cargo ship and the grain silos, it really does kind of increase linearly with the size. So we're doing it per megawatt hour. So obviously, if you want a lot of metal, it still will be a significant cost. It's just proportionally to the other costs. It's pretty much negligible.
Yeah.
I was wondering, how do people show what kind of technology?
There's a couple of different lab groups, but I think that we're one of the few.
One of the fascinating things for me also knew was the different heat content for zinc versus the other metals. And that I was just wondering as a criteria, as you're looking at something that you deploy more broadly, that might make a difference, even though the cost issue is a huge kind of drawback.
Yeah, certainly. I mean, you're going to need 5.8 times the boats, the storage, everything. I think that one would be preferable. So one of our companies actually mines zinc directly. So for them, it might be more suitable because they already have it on hand. In terms of actually being an energy carrier for somebody who doesn't mine the metal themselves, they'd definitely be looking more at aluminum, like you said, for to have the best energy density.
All right. Thank you very much. We now have the coffee and tea break scheduled, and for everyone to listen here at the beginning, we had one person wasn't available to do those.